Section 2.3 is titled Other Set Operations. And the first set operation we're going to talk about is the set intersection. So a set intersection is the set of elements common to both sets. I'm going to draw a Venn diagram to talk about that first. And we'll take a look at how that can be thought of in a context question as well. So a Venn diagram starts with a box, right? Rectangle. And we're going to put two sets inside of it that overlap. So there's going to be two overlapping circles. Okay, so this box on the outside is called the universal set. We're going to label these A and B. And if we're talking about the set intersection, we're talking about what they have in common, this is the overlap we would be referring to. Okay, the overlapping piece. The notation for this is an upside down U. Or you can think of it as looking like a lowercase but big N, a little n. We talk about set intersections all the time because you talk about street intersections. That's exactly what an intersection is at a street. It's the part where the two streets have in common. So when we talk about the intersection of MacArthur and Kickapoo out here, we're actually talking about the part that's in the middle, right? Not the streets that are coming into, but the very center part, what they have in common. So if you were talking about, I'll do that example in a minute. Let me pause on that one. Let's do union next. Okay, so a set union is the set of all objects in one set or the other or both. So let's draw again a rectangle with the two circles inside. Label them A and B like before. And the union means that it's including everything. So we get all of circle A and we get all of circle B. One set, the other, or both. And the notation looks something like this. A, U, B. So U for union. Okay, the union one that I always like to give an example of is we call marriage a union of two people, right? Union means I get everything you have, you get everything I have. Okay, so if somebody comes into the marriage with kids, they're not my kids and your kids. They should become our kids. It's not my debt and it's not your debt, it's our debt, right? We get all of it. So that's what happens when you get married. It all becomes one big pot of whatever was happening before. It's just all together now. Okay, that's a union. And that's what happens when we talk about union with Venn diagrams as well, or sets. We get all of it. Okay. There's one more. It's called the relative difference. The relative difference is the set of all elements in one set that are not in another set. Okay, a Venn diagram again. Draw our rectangle and our two circles. So relative difference looks like subtraction. So I'm going to do A minus B. We're going to go back to the slides before. I'm going to write something else out in a minute here too. So everything that's in A and it's not in B, which means it ends up looking like this sort of half moon thing going on here. So that's taking what we have in common and removing out what one of us has. Removing out what one of us has completely, including the things that we have in common that we share, right? We remove those pieces out. It's what I only contribute, what I only am talking about for me personally, or for my set personally. All right, let's go back here. I'm going to actually write these out in set symbols so that you can see what they look like. So what does A intersection B actually mean? Well, it means it's the set of all x such that x is an element of A and x is an element of B. It's an element of both of them. The key word you hear used a lot with intersections is and. And. Which sounds kind of like conjunctions, doesn't it? Yes, it does. So if intersections are like conjunctions, what do you suppose unions are like? They are. They're like disjunctions. So this is the set of all x such that x is an element of A or x is an element of B. It's not saying either or exclusively, so it could be both. But as long as it's categorized under one or the other, we're good. It gets included. If it's in A, it's in B, it's in both. Any of those. We are in the union. All right, the relative difference then, the last one here that we've talked about. So this is the set of all x such that x is an element of A and x is not an element of B. It's included in A and it is not in B. Okay? This would be almost like the stuff that happens when people get divorced. Like, right? This is the stuff that you brought in. You get to take it out for sure. It's the stuff in the middle that starts to be questioned. All right? But this is the part that was yours for sure before. And we're going to do an example. This is a blended family because blended family is a perfect example for this description. Consider Mary, single mom to one child, Mark, and Joe, single dad to two children, Jack and Jill. Mary and Joe get married. Together they have two children, Ann and Andy. If M equals Mary's kids and J equals Joe's kids, find and describe the following. Okay, is everybody with me? Okay, so what is the first symbol that's used here? What is that symbol? Intersection. Intersection means and. It means in common. So what do Mary and Joe have in common? So what would that be? In fact, I'll write that out too. These are the kids in common. And we're thinking biologically, not how they feel about them emotionally, because then we could just put them all down on everything. That's not what we're doing, okay? So we're talking about biology here, okay? Biologically. So what kids do they have in common? Ann and Andy. You got it. All right, what about the second one? What's that symbol mean? Union. So what it really means is everybody, right? This is all the kids. Okay, so who gets included? Well, Ann and Andy do automatically, right? They were in the intersection anyway. Who else gets included? Mark. Joe's the dad. It's okay, it's worded a little, it looks a little funny on my screen. Who else? Jack and Jill. What is C saying? So these are the ones that belong to just Mary. So this is, heaven forbid, the kids that, were they to split apart, she would still have some sort of legal rights to see, right? Just Mary's kids. So who gets included here? Mark, Ann, and Andy. Are we sure? I think I said that is not right. I totally misspoke when I said the statement earlier. Let me reword. Let me rewrite. Only Mary's kids. I got carried away. This is not the people she has the legal right to see. These are the people she started out with, right? Just Mark. I'm sorry. Should look at my notes every now and then. It's a good idea. Just Mark. Mary's kids that are not Joe's kids is what this should be. This is just Mark. Okay. Are you guys ready? there are some cool properties about sets that we're going to see first. The first one's called commutativity. So some of you have seen commutativity more. Do you remember what commutativity means with numbers? Anybody remember that one? We're going to encounter this further. I mean, we're going to keep encountering commutativity over and over again. With numbers, addition and numbers is a commutative property. So commutative means you can switch the order. So like 5 plus 3 is equal to 3 plus 5. Okay, so that's a commutative property. So with set intersections and unions, it looks something like this. So we're going to be able to do this for all sets A and B. The union of A and B is the same as the union of B and A. And the intersection of A and B is the same as the intersection of B and A. And just in the very way that we shaded things in our diagram, there's nothing about that that matters on which order they were in, right? There's not. They're also associative. So associative has to do with how things are grouped together. So this is for all sets A, B, and C. So if I were to do the union of B with C, this would, and then the union of A after that, this would be the same as taking the union of A first and B, and then doing the union of C afterwards. An intersection works the same way. If I do B intersect C and then I intersect it with A, that's the same as doing the intersection of A and B first, and then the intersection of that with C. Now, you'll notice there's not one that says the relative differences do that, right? I can't switch the order. B minus A is not A minus B. It doesn't work. I mean, just picture-wise, you can see that that's not going to work. If we went back over here and we did J minus M, right? Joe's kids that are only Joe's kids. That would not be the same as Mary's kids that are only Mary's kids, right? So the orders of those things matter. The last one is the distribution of set intersection over set union. So let me show you what that looks like. Same description as before. This is for all sets A, B, C. And this one is talking about what happens when we have the intersection of A with B union C. We could do the intersection of A with B and the intersection of A with C, and then do the union. And that should feel like the distribution property that you are familiar with multiplication, right? If you had a multiplication outside addition, you can multiply across the parentheses and then add when you're done. This has that same flair, the same feel to it. So you can take the intersection of A with B, the intersection of A with C, and then do the union afterwards instead of doing it before. All right, and then let me talk about the cardinal number formula. The cardinal number formula, remember cardinal numbers talk about how many things are in a set, not the sets themselves, but the number of items in them. This cardinal number formula talks about how we can count the number of items in a union. If you're finding the number of items in the union of two sets, you can find the number of items in set number 1, or A, the number of items in set number B, and this is going to feel awkward, just write it down and then I'll show you a picture of why it makes sense. And then you subtract the number of items in the intersection. And what I'm going to show you isn't exactly a proof, but it's definitely a justification for why this is a reasonable formula to have. So let's draw ourselves a Venn diagram to support this. Set A and set B. And there's a set U on the outside. I'm not even going to use numbers with it. I'm going to use some shading to show you what's happening. Right, so if you counted all the items in set A, you'd be counting everything inside of the circle of A, including the part of the overlap, right? That would be all the number of items in set A. And then, if you counted all of the items in set B, you'd be counting everything in circle B, including the overlap. And what do you see would have happened? Yeah, the overlap part got counted twice, right? This is exactly what would happen if we go back to Mary and Joe over here. How many kids does Mary have total? How many kids does Mary have total, biological kids? 3. How many biological kids does Joe have? 4. But they do not have 7 kids together, right? So you'd have to subtract out Ann and Andy because you counted them twice. You counted them when you counted Mary's kids, you counted them when you counted Joe's kids. So this is the cardinal number formula. You're subtracting out an overlap. It's the double counting. Right? It's the same thing that happened when we did the problem with handshakes. We didn't do it with handshakes. We did it with the games that people played on a soccer field or something like that, right? We had to eliminate the overlap, the double counting. Okay? This is the same idea. The last set operation that we're talking about today is called a Cartesian product. All right, so the Cartesian product is the set of all ordered pairs such that the first component comes from the first set, the second component comes from the second set. So I need to create some sets and make some sense of this with you. So we're going to call set A as having the elements X, Y, Z. And we're going to say that set B has the elements 1 and 2. And yeah, I know one of them's letters and one of them's numbers because I want you to really clearly see where the things are coming from. The Cartesian product tells you how to count elements. I'm sorry, I'm going to do the counting second. The Cartesian product tells you how to organize the elements in the set. It looks like an X, kind of like multiplication. It's not multiplication, but that's what the symbol is. And what this does is it creates pairs of elements. So one possible pair would be X matched with 1. Element from set A, element of set B, X and 1. But X doesn't have to be matched with 1. X could be matched with 2. That's the only pairs that X can have. What about Y? Well, Y could be matched with 1. Or Y could be matched with 2. Notice there's not necessarily a one-to-one correspondence like we saw before. It's not what we're talking about. We're not actually pairing these people off. We're just talking about the pairings that are possible. We could have Z with 1. Or Z with 2. And these are all of the possible pairings that there are. And each of these pairings creates a set. It's a set of ordered pairs. Okay, and that's called the Cartesian product. Here's what I wanted to show you about the Cartesian product. There is a formula. We're going to count a few things here. So tell me, how many items do we have in set A? N of A is what? 3. What is N of B? 2. And what is N of A cross B, the Cartesian product? It's 6. What relationship do you see that appears? It's a multiplication property in there, isn't there? And there's actually a formula that says that the number of items in the Cartesian product, not the items themselves, but the number of items in the Cartesian product, is equal to the number of items in set A times the number of items in set B. This is a cardinal number formula. It doesn't talk about the elements. It just talks about how many of them there are. All right? So notice and be very careful when you're looking at problems like these. If something asks you to find A cross B and you give me the answer 6, you didn't find A cross B, right? You found the number of items in A cross B. If the problem asks you to find the number of items in A cross B and you find the set and you list them all out, but you fail to say there are 6 of them, you again failed to notice the notation. So be careful with the notation on this. Okay, and we're going to stop right there for today.